Swayam Prabha, Digital India, Educated India.
So we are continuing our discussion from previous class. Now bend velocity is basically is obtained from the slope of EK diagram, right? And we have already realized that group velocity is 1 over h bar d by dk, right? Now this is basically 0 at these zone boundaries, the integral multiple of pi by a plus b, right? And a plus b is basically, you can say, it's a translation vector r, right? So when they are folded, so for example, you have this bend here, then you will see here, this is 2 pi by a plus b, so you can shift it here. This is 2 pi by a, you can shift it here, so you get one bend here. This is pi by a, so you have to actually shift it here, right? So this will shift here, so you will get something like this, and this will shift here, so you will get something like this. So you will have one bend here, right? So these are basically resulting from the reduced zone, right? Otherwise, actual EK diagram is like this only, right? This is for free electron, and this is for electron in the crystal. So when we, because these k vectors, which are differing by 2 pi by a plus b, they are identical. So we can always represent this thing as a reduced zone. So period is 0 to 2 pi by a plus b, right? So for convenience, we actually use minus pi by a to pi by a plus b to plus pi by a plus b. And if you look at d by dk, this is the slope of EK diagram. Now, for example, if you consider this free electron, right? What is happening to the slope? Slope is 0 here, so the velocity is 0. Slope is high here, slope is even higher here, right? So as you move away, your slope is increasing for free electron, right? Now if you see here at these boundaries here, again the slope is 0, right? At the integer multiple of pi by a plus b. So again the velocities are 0 here. And if you see here, this is positive, so velocity is positive. This is negative, so velocity is negative, right? Again, this is apparent because of zone folding, right? So this velocity concept is clear. To another important concept called effective mass. So if you see this picture on right side actually shows the typical bend structure, right? So typical bend structure is not always parabolic, but what we do at the bottom of these bends or the top of bends curving down, we can approximate these curves as parabolic, right? So this is an approximation. Now why this approximation is valid or makes sense? Because when electrons fill these orbitals, these energy bands, they usually occupy this bottom of the band. So this is basically parabolic approximation at the bottom of the band or the top of the band curving down. They would name basically the band which is curving up, we call it conduction band, and the band which is curving down, we call it valence band. We can recall that group velocity is 1 by h bar d by dk, right? And the momentum of electron is p equal to h bar k, right? So if the electron in the crystal, it experiences a force, right? So what will be the corresponding behavior of the electron in crystal? How it will be different from the free electron? So you can always write force is equal to dp by dt, right? Force is equal to dp by dt, and p is h bar k. So you can write force as h bar dk by dt, right? And force by mass is dv by dt. So this v is a group velocity. So dv by dt you can get from here. Now there is no t here. So what we can do? We can use the mathematical technique. We can differentiate dv by dk and dk by dt. Right? Now dv by dk will be 1 by h bar d2e by dk square. Right? And dk by dt is, from here you can get f by h bar. Now this is acceleration and this is equal to f by m. So when we compare it, we get 1 by m is equal to 1 by h bar square d2e by dk square. Now what is d2e by dk square? It is a curvature. So that means if you have a parabola like this, its mass is, let's say, m1. If you have parabola like this, its mass is m2. So which is greater, m1 or m2? Which will be greater, m1 or m2? So there are two parabolas, right? One is sharp parabola,
M2.
m2, right? Why? You can write the
Because here
equation of parabola h bar k square by 2m, right? If it is mass is more, see, you start from 0 here, right? For same k, if mass is more, e will be less, right? You can see here. So this one has less curvature. Or d2e by dk square is h bar square k square by 2m. So d2 by dk square will be h square by m, right? So if m is less, double derivative is more, right? So sharp curvature. So for smaller m we will have sharp curvature. For larger m we will have not so sharp curvature, right? It will be more broad. Now let's say your wave function, this ek diagram is like this. What will be the mass? m3. What will be m3? It's a flat line, so E is constant with K. So there is no variation with respect to K. What will be the mass?
Infinite.
infinite.
Very good. So mass will be infinite. Now if it is curving down, what will be the mass? If a parabola is curving down, what will be the double derivative?
Negative.
How do you obtain the face of the parabola? Is double derivative will be positive or negative?
Negative.
Negative, right? So if it is curving down, the mass will be negative. Again, if it is curving fast, so again this mass will be at least magnitude will be less here, magnitude will be more here, right? But so we have positive mass, zero mass, and then infinite mass and negative mass, right? So that curvature of Ek gives us the property of mass, right? Now what is the meaning of negative mass? Negative mass means if we apply a force, right, and force equal to mass times acceleration. So if force is in direction, let's say x, if mass is negative, then acceleration will be in direction of minus x, right? So why electron will wave like this? You can see here. If it is curving down, then as the k vector is increasing, energy is decreasing, right? So here basically what we write, energy as let's say this point is EV. So energy is EV minus h bar square k square by 2m, right? So we have taken this m negative sign of the m outside, right? So we write it h bar square k square 2m. Now this m is, now this m is actually positive because we have taken this negative sign outside. If you recall, we have drawn this one. You can see a John folding, right? So as the energy is increasing, k is increasing. See, you see here this curve. As energy is increasing, k is increasing. But due to the John folding, what is happening? This guy shift here, right? So here it appears that as k is increasing, energy is decreasing. You see here when this guy folds here, right? As k is increasing, energy is decreasing, right? So this is basically kind of looking from the wave vector. It is a view from the wave vector. So that means if wave vector is increasing from pi by r to 2 pi by r, right? But for the atoms in the crystal, it appears that wave vector is actually decreasing from minus pi by r to 0. You understand? It is increasing here, pi by r to 2 pi by r. It is actually, this change is same as minus pi by r to 0 when we translate it to the Brilliant zone. So it appears that this k is actually decreasing, increasing here, decreasing here. Magnitude is decreasing here, or this way. Correct? Physically, if you see, it is actually a mathematical representation of physical thing. See, let's say there is a wave vector pi by, I'm writing r equal to a plus b, right? You give energy to it, what will happen? It will increase, right? Let's say it will become pi by r plus some delta, right? Now when the crystal looks at this wave function, what it will look? For pi by r, it will look as plus pi by r minus pi by r will be same. Pi by r plus delta, it will look at minus pi by r plus delta, right? Or pi by r minus delta, because they are basically same. As far as potential distribution seen by these electrons, that's what we discussed, right? For wave vector outside the Brilliant zone, the potential seen by these electrons is same as corresponding wave vector inside the Brilliant zone. So for let's say 0 to pi by r, wave vector increases. Pi by r to 2 pi by r, wave vector increases, but corresponding wave vector here is decreasing. Then 2 pi by r to 3 pi by r, it is increasing, and this is increasing here also. So you understand? So for 0 to pi by r is increasing, pi by r to 2 pi by r decreasing, then 2 pi by r to 3 pi by r again increasing. So it's basically periodic cycle is taking place. Or additionally, you can see basically atoms in the crystal, they are at discrete positions, right? So potentials are at discrete point. So particular wave vector and wave vector plus integer multiple of 2 pi by r, they actually see the same potential. It's like sampling, right? They see the same potential. So for as far as crystal is concerned, it doesn't discriminate between the two wave vectors. So as the wave vector is increasing inside the Brilliant zone due to the sampling, sampling type of situation, it appears to decrease. So by this possibility, we have both positive mass, negative mass, infinite mass, right? What will be zero mass? Zero mass will be just vertical line, right? No opening, right? So that is usually not found, but all these positive, negative, infinite mass are actually found. Now, infinite mass will correspond to a situation where now if a particle has infinite mass, now will that particle move? Particle with infinite mass, will it move? It can move with constant velocity. So if there is initial velocity 0, now can it move? Other reference? No, we are talking on this particular reference. So if a particle has infinite mass, then its acceleration will actually be 0, right? So that means this kind of EK diagram, where there's a flat line, it will correspond to a band where particles don't move, right? That means particles are confined. So this is called basically like an impurity level, right? So in that band they cannot move. Once if they acquire energy and they change the band, then they can move. but in that particular band they cannot move. So they are basically localized carriers. Right? Okay. Now just to remind you that these properties, effective mass and group velocity, they are important near the top of the valence band and the bottom of the conduction band. Now I'm just repeating it, that bands which are curving up, they are called conduction band. Bands which are curving down, they are called valence band. Now here is basically one cartoon again, which shows this is curving up, positive mass, little less, then flat, infinite mass, it's negative mass, right? So this basically effective mass, it parameterizes the difficulty faced by the electron in running through the potential. Right? So again, this is exercise for you. You can try plotting E is equal to h bar k square by 2m for positive, negative, 0, and find value of m. Right? You will actually be able to reproduce this kind of curve. Now, how these carriers move? We can consider two types of situation, right? Let's say band is full, right? Let's say band is empty, right? Now, what is J? J is equal to rho times V. So charge density times velocity. If the band is full, what will happen? If the band is full, right? Then for wave vector k, there is a wave vector minus k also. So for every wave vector k inside the Brillouin zone, there is a wave vector minus k also, right? So they will actually have the velocity, or we can say phase velocity. Phase velocity is h bar k over m, right? So this individual velocity of each particle, they are basically cancelling out each other, right? So for each particle with k vector, we have another particle with minus k vector. So overall, their velocities will add up, and you will get zero current, right? So if the band is totally full, you can compare this situation to a jar of water which is full. So when you rotate the jar of water, what do you get? You will not observe any net movement of the charge or net movement of water, right? So there is no current, right? So that is what is happening in a full band. An empty band, of course, there are no carriers, so current cannot flow anyway. So both filled and empty bands, they do not carry a current, right? Now here we are considering a one-dimensional situation. So rho is basically Q by L. So charge per unit length, you can say. Okay. Now if there is a band which is partially filled or partially empty, so for partially filled band, again you can write rho times V, so Q by L times Vi. So only the particle which are there, they will take part, right? For empty bands, let's say this band is full, only one electron is taken out, right? So you can write that current will be Q by L times all Vi, right? Now if one particle is taken out, then that current we have to remove, right? So only the empty part we have to write, and then now this empty part is basically, if you see here, let's say this is a crystal, right? And this electron here goes to right. Now we have taken away this electron, right? And corresponding some other electron, let's say you have blue electron. This is blue electron, right? So blue electron come from position 2 to position 1, right? Now let's say we have taken out the red electron, right? Red electron is not there, and the red electron velocity is, let's say, v1, right? So due to this, red electron velocity is minus e times v1, right? And due to blue one, it is minus e times v2, right? Now this part is not there, right? Because EV1 was compensated by EV2. So if red electron is missing, you will have EV2 uncompensated, right? EV2 will be uncompensated. So that will give the current. Now the direction of V2 is minus V1, right? So you can write minus EV2 as plus E times V1, because V2 is minus V1. So this it means that empty charge, right? Empty charge is moving with velocity V, is carrying a current EV1, right? So it, for a partially empty band, it appears that those vacancy, right? Vacancy of electron is carrying the current. So when the vacancy is moving with velocity V1, it is giving out a current of plus E times V1, right? So it is as if a positive charge is moving instead of negative charge. Or you can understand in another way. Now this band is curving down. So this band has negative mass, right? So we have negative charge and negative mass. And equivalent situation will be a positive charge with positive mass. So holes are basically representation of vacancy in this empty valence band, where you can write this hole as positive charge with positive mass. So L is basically, we are considering 1D case. So this is length. So charge per unit length you can say, because J is rho times V. So for 2D, it will become L become area. For 3D, it will become volume, right? So this is a charge density, because J is a current density. If I add I instead of J, then it will be just Q times V.
Sir, can you repeat this part, please?
Okay. You consider a red electron and blue electron. Red electron moves from position 1 to position 2. Blue electron moves from position 2 to position 1. So that means current due to red electron is minus E times V1. Current due to blue electron is minus E times V2. Now we have taken out the red electron. So red electron is not compensated. That means minus E times V2 is the charge movement, which is not compensated. Now V2 is minus V1. So minus EV2 can be written as E times V1. So due to this empty charge here, the red electron, we are having current E times V1. Now E is the charge and V1 is the velocity of this empty space, right? Or hole we can say. So if we have number of holes, then they all will add up basically. So that will become Q times all the empty holes added up with their velocity. Correct? This is a concept of hole basically. So electron in the conduction band, they have positive mass. Electron in the valence band, they have negative mass. So this negative mass and negative charge electron can be replaced by a empty space for with positive charge and positive mass, and that is a concept of hole. This is clear. So we have discussed three concepts, right? Group velocity, effective mass, and the concept of hole, right? In the bands which are curving down. Now, so far we have discussed this thing in one dimension, right? Now in three dimension, how the situation will look like? Because in three dimension we will have more symmetry points. Here we only consider 2 pi by r or 2 pi by a plus b, right? In three dimension we have three vectors, a1, a2, a3, right? So how we can represent a 3D crystal or 3D unit cell, and how the wave vector will look like for 3D unit cell, right? So as you can recall, if the dimension in real lattice is A or R, in reciprocal lattice it is 2 pi by R, right? So this is basically very much like a Fourier transform, right? So for example, you have periodic potential A here, right? Then we said that this Brillouin zone is from minus pi by A to plus pi by A, right? Or 0 to 2 pi by A. Basically, periodicity is 2 pi by A, right? So this is basically your real lattice, and this is reciprocal space or called K lattice. Now this is for 1D. In 3D, let's say A1, A2, A3 are the lattice vectors. So corresponding reciprocal space vectors can be obtained by this expression. So A2 cross A3 will give B1. A3 cross A1 will give B2. A1 cross A2 give B3. This is of course divided by the volume of the cell. A3 dot A1 cross A2. So these three are actually equivalent. A1 dot A2 cross A3 is same as A2 dot A3 cross A1 is same as A3 dot A1 cross A2. So here A1, A2, A3 are the lattice vectors, and B1, B2, B3 are the reciprocal lattice vectors. They are reciprocal lattice vectors. Now I will give you some practice example to do. What you can do, all of you know FCC, right? FCC has the lattice point at the faces, right? And you can recall that in one of the lecture we defined the lattice vectors for FCC, right? They were actually pointing to the faces, right? So this is, let's say, X, this is Y, this is Z, right? So this is AY2, AY2, comma 0, right? This is 0, comma AY2, comma AY2, right? By here, this is X and Z. So AY2, comma 0, comma A2, right? So these are the three lattice vectors for FCC. Now you apply this equation here and calculate the reciprocal lattice vectors. So for FCC lattice, when you apply this, you will get reciprocal lattice vector pointing to the three body centers. So first quadrant and other two quadrants, right? So for FCC, you will get a BCC crystal. So an FCC crystal in real lattice will give a lattice point in reciprocal space, which will look like a body-centered cubic. Is it clear? Let's say you have FCC lattice and you have these lattice vectors. You calculate the reciprocal lattice vectors, and when you translate those, basically you obtain B1, B2, B3, and by M1, B1, M2, B2, M3, B3, you reproduce the whole lattice. It will actually look like a BCC. So this one you try and calculate these wave vectors, right? So for FCC lattice, because our silicon, germanium, gallium arsenide, they all have FCC lattice, right? So their reciprocal space will look like a BCC lattice, right? And then in reciprocal space, we can calculate the Wigner seed cell, right? Can you recall how do we calculate the Wigner seed cell? What we do? So for FCC, what will happen? You will have these corners, right? And then you will have another atom in the center, right? So we can, let's say, use red here. So there's another atom here, lattice point here. So that will be BCC, right? So these red will look like BCC, right? Now, how the Wigner seed cell is calculated? What you do, you connect these two nearest lattice atom and draw a perpendicular bisector. Then here also you draw a perpendicular bisector. Now this is basically you will have another body here. So perpendicular bisector will be at the face here, right? Right. So your brilliant zone or Wigner seed cell will look something like this, right? So here you see this hexagon is basically is a plane perpendicular to line joining the center and the corner, right? So what is the length joining the center and the corner? And by the way, you will also find out that if the lattice constant is a here, in reciprocal space it will be 4 pi by a. So distance from center or body center to the face will be 2 pi by a. So for x vector, so this is called gamma, right? Gamma is basically the center lattice point, right? Or it's called 0, 0, 0. So 0, 0, 0 k vector, right? And this x is, you can say 1, 0, 0, or because this is y, so you can write 0, 1, 0, right? Okay. Now what is the distance? It will be 2 pi by a, right? So your x will be, the coordinates will be 0, 2 pi by a, comma 0, right? Because y and z they are 0, only x direction is there, it is 2 pi by a. Similarly for L is along the diagonal, right? So diagonal length is 2 pi by a times root 3, and half of that is root 3 by 2, right? So that is 0.872 pi by a, right? Or you can say root 3 pi by a, right? So for L, so length of the L is root 3 pi by a, right? So now this root 3 pi by is along the diagonal, right? So if you take the component x, y, z component, you will get pi by a, pi by a, pi by a, right? And the length will be root 3 pi by a. Similarly, so this W is basically is the intersection of the plane with the plane at the face and plane at the this along the diagonal, right? So plane intersecting the diagonal and plane intersecting the face, they are meeting here at W. So W is basically, again, x is 2 pi by a, and y is, this is again pi by a, and there is no movement along perpendicular direction, right? So 2 pi by a and pi by a. So here you see W is 2 pi by a and pi by a. Now it appears that here x is pi by a, but here it is actually z. So z is pi by a. That means there's equivalent face here. So this is also W, right? So there will be 4 equivalent W's there, right? So they all will have 2 pi by a, right? So you can select all 6 faces, right? So there are 6 faces. Then this will also be same as W, right? This bottom will also be as W. This will also be W, right? So this is 2 pi by a, and this is plus pi by a. This is minus pi by a, right? So basically, you can get equivalent wave vectors corresponding to these intersection points of the planes. Similarly, U is pi by 2a in z direction, pi by 2a in x direction, right? So this is pi by 2a, and y is 2 pi by a. And similarly, you can get k also. K is the intersection of planes bisecting these 2 diagonals. So 2 adjacent diagonals are bisected. So that will give k. So k is basically again it's 3 pi by 2a, right? So this here is 3 pi by 2a. So again in z direction is minus 3 pi by 2a. X direction 3 pi by 2a, right? And y direction nothing, right? So you have basically only two axes. Along two axes you have 3 pi by 2a. So this is k, and this will also be k. This will also be k, right? This will also be k, right? So these are equivalent k directions. So most important ones that we will deal with is gamma, x, and L. Now x is called 100 or 010, right? 100 direction, and L is called 111 direction. Okay, so please remember these three only, gamma, x, and L. 100 direction and 111 direction. Correct. So what we have learned here, for the FCC lattice, when we take the transform and we move to reciprocal space, we get a BCC. For BCC, we construct a beginner seed cell, and then beginner seed cell we get different symmetry points, right? See, ideally we have to calculate the EK diagram for all the k vectors, but there will be infinite number of k vectors, right? So we cannot draw EK for all of them. It will be difficult to visualize. So what is done? We draw this EK diagram for definite symmetry points, and especially 100 and 111, right? So then we can represent it using a 2D diagram. So for example, here you see the EK diagram for gallium arsenide. Now you notice here it is not symmetrical because plus k and minus k are not same here, right? That is because this direction is 100, this direction is 111. If you draw 100 or minus 100 here, then it will be symmetrical. Okay. Now you notice one more thing here. This is balance band. So all these three are balance band. 1, then 2, and 3, right? Now 1 is basically has bigger curvature. So this is called heavy hole. Second is less curvature, it's called light hole. And this has another name called split off. Now there is a curvature, this curving up, right? This is called conduction band. Now you notice here, now same curve is curving up here, it is curving down here, right? So it is basically, if you look at particular position, right? The same curve may be part of the conduction band, may be part of the valence band. But what is important here is the Fermi level. The Fermi level is the energy level up to which these energies are filled. So if Fermi level is somewhere, then only the nearest band edges are important, right? So the concept of Fermi level we will discuss either in today's class or tomorrow's class. But for now, you take Fermi level as the energy level up to which states are filled, right? So that means all these EK diagram. So all these states, K wave vectors are basically states, you can say. So they are filled. So you have holes, and you have holes in the valence band, and you have electrons in the conduction band. So this gap between these two band edges is called the band gap, right? So here you see the difference is 1.42. So that is the band gap. Now you notice one more thing here. There is another valley here, right? So this is also conduction band. Another valley here, this is also conduction band. But the gap here is 1.71, here 1.9, right? So their energy is more. So if electron gets some energy, it will preferably go to the valley here at gamma, right? So this is all called gamma, right? So let's say this is particular band 1, right? This is band 6, right? So this is for band 6, you have one valley here, so this is called L valley, right? Because this is 111 is called L, 100 is called X, so this is a L valley, and this is 00 is called gamma, right? So this is called gamma valley, and this is called X valley, right? So we have 3 conduction bands, right? L6, gamma 6, and X6, right? 6 is basically the band number. So you have 1, 2, 3 like this. They are different bands, right? So another thing you can notice here, because the conduction band, the minimum of the conduction band and the maximum of the valence band, they are exactly at the same wave vector, gamma, right? So that means such materials are called direct band gap. So this is a concept of direct band gap. So direct band gap materials are those in which bottom of the lowest lying conduction band and the top of the valence band, they have the same wave vector. Okay, these holes correspond to empty state and concave down. Correct. Sir, what is the use of reciprocal lattice? So that's what we are discussing now. Okay, any other question? So from reciprocal space, basically, we get all these band structures, because we have defined these wave vectors in reciprocal space only. So no question? Okay. Then we can look at other band structures. So these are the band structure for germanium and silicon. So again, heavy hole, light hole. Okay, this is heavy hole. We see only 2 bands here. What does it mean? In case of silicon, we are seeing 2 bands here only, right? So this is heavy hole, and this will be split off basically. So that means heavy hole and light hole, they are basically coinciding. So they have similar, exactly similar mass, right? So this will be split off. Now the difference between split off and light hole, heavy hole is that light hole and heavy hole, they have the same energy at the upper edge. So very simple. There may be very minute difference here. And split off has some energy gap here. So this will be split off, and this will be light hole. So this is, sorry, heavy hole. This is, and this is light hole, and this will be split off. Split off is not shown here. That means, okay. For gallium side is shown here, right? So heavy hole, light hole, split off. For germanium, heavy hole, light hole, and split off. So if you want to identify split off, there will be a gap here, energy gap here, right? Generally, heavy hole and light hole have same energy EB at their top of the band. Now look at the conduction bands. In case of germanium, the lowest lying conduction band is at L, right? So this L valley is the lowest lying, right? So the maximum of the valence band appears at gamma, and the minimum of the conduction band appears at L, right? So this will be a indirect band gap. Similarly, in case of silicon, minima appears at along the X, is not exactly at the X, but slightly before the X. And the maximum appears at gamma, right? So this will also be a indirect band gap. In case of gallium arsenide, both valence band minima and the conduction band maxima, they appear at the gamma valley only. So they are called direct band gap, right? Now it is important to know how many such valleys are there. For example, in case of silicon, right, the valley appears at the X, right? So in case of reciprocal space, how many X valleys will be there? Now X is corresponding to the phase, right? So you can see here, X is corresponding to the phase. So how many phases are there in a BCC lattice? Because BCC is a reciprocal of FCC, right? So For any cube, BCC cube, how many faces are there? 6. So that means there are 6 equivalent X values. And for germanium, we recognize there is a value at L. So L is along the diagonal, right? So how many equivalent L values are there? So how many corners are there? 8 corners, right? So there will be 8 L values. So you can see here, germanium has 8 L values and silicon has 6 X values, right? So when you are going to count the number of states or number of carriers, or when you calculate effective mass, so that effective mass we obtained a double derivative of d2e by dk square. That was for particular band. So when you have to calculate for all these 6 or 8 equivalent values, you will have to add them together, right, in a certain fashion to calculate the actual effective mass of the carriers, right? So they will come into, number of values will come into the picture when we will calculate the density of states, right, or density of state effective mass or conduction and effective mass. So they will come into the picture. Right now it is clear. So we have discussed the band structure of 3 materials: germanium, silicon, and gallium arsenide. Germanium and silicon are indirect band gap because their bottom of the conduction band appears at L value and X value respectively. In case of gallium arsenide, their bottom of the conduction band appears at the same position as the top of the valence band, called gamma valley, and therefore this is direct band gap semiconductor. Okay. Now this is a more complete picture. This is for germanium along the edges. This is for silicon along the faces, and this is for gallium arsenide at the middle, right, or gamma valley. Now what we said effective mass is 1 over m is 1 over h bar square del 2 e by del k square, right? But here we assumed while driving that effective mass, we assumed that ek is parabolic, right, or it's a paraboloid, right? Now it is possible that if you look at the parabola, right, in x direction it may have certain curvature, in y direction it may have another curvature, right? So when you rotate it, right, so in x direction curvature is let's say more, in y direction curvature is less, right? So they may have different curvature. So this is along x direction and this is along y direction, right? That means its mass along x direction and y direction will be different, right? So that means if you apply a force in certain direction, right, we have to consider the mass along that particular direction, right? So that means your effective mass is actually a tensor. Now how it is tensor? The force is equal to m times acceleration, right? So acceleration is dv by dt, right? So let's say you apply a force in x direction, right? Let's say we are applying a force in x direction, right? Now that electron may be accelerated along x direction, right? So if electron is accelerated along x direction, then force will be mass times acceleration, and mass will be, we call it mxx, and mxx will be 1 by h bar square d2e by dkx square, correct? Now if we apply force in x direction and say electron is accelerated along y direction, right? How it is possible? You apply a force in x direction and electron is accelerated in y direction. This happens in a constraint situation. When there is a constraint, then actually, particle can move in direction which is not along the force. For example, you have some plank here, right? So let's say you can recall as just a wooden plank here, right? And you have a mass on that plank. Now, if you apply force along the plank direction, it will move in the same direction. If you apply a force, then it will have two components: horizontal component, or you can say normal component, and inclined component. So due to inclined component, it will move, or perpendicular component, it will not move. So overall direction is you are applying force in this direction, and movement is along the plane, right? So it will have two components, uh, along the force and perpendicular to the force, right? So that means this wooden plank is moving as acceleration in the two direction of force and perpendicular to the direction of force, right? Similarly, in the crystal, due to this periodic potential, electron can move in a direction which is perpendicular to the force. So it will have certain component along the direction of force, or Q times E, and certain component in direction perpendicular to the force also. It is possible, right? So let's say if you apply force in x direction, electron moves in y direction, right? So in that case, how will you give the effective mass? So that will be m times yx, right? So it will be d2ey dkx dky, right? So that way, when you permutate, you will get a tensor, right? So for force in x direction, you will use mx, myx, mzx. Force in y direction, you will use myx, myy, myz, right? So this is your effective mass tensor. Now, having said that, if these x, y, z are particular direction or principal axes, if these x, y, z are principal axes, then these cross components will not be there. Only the diagonal elements will be there. So this is a property of principal axes, right? So I will not go into the detail, but this is just for information that if x, y, z are principal axes, then this effective mass matrix or tensor will be diagonal will have only diagonal elements, right? Otherwise, this will be basically full matrix. For example, you have this EK diagram, right? So you can write EK is E0 plus H bar square K x minus K0 x square by 2m. So you can write for 3D. So if your x, y, z directions are same as this direction here, you can calculate the effective mass tensor, and it will have only diagonal elements. If you change the frame, let's say you define your x, y, z to be some other thing. Let's say this is x, this is y, this is z, right? So this is your x prime, this is your y prime, this is your z prime. So if you calculate this effective mass tensor along this x prime, y prime, z prime frame, then all the elements, it will not be a simple diagonal matrix. Means non-diagonal matrix will also be non-zero. So we rotate it basically, right? So here x, y, z will be principal axes, and rotated axis will be generalized axes. Right? Clear? Now these band structures are very useful in a sense that they give us a lot of parameters, right? So for example, you can get a band gap. So if you are able to calculate this band structure, then you can get the for silicon is around 1.1, for gallium arsenide, for germanium around 0.67, for gallium arsenide around 1.42 or 43 electron volt. Then you can also calculate the mobility of electron and hole, effective mass of electron and hole, right? These are the lattice constant, these are dielectric constant, this is the density. Density you can calculate from the crystal structure, right? And these are the melting points, right? Again, depends on how tightly they are bound, right? So from the constant energy surfaces, so these are basically equation of the surface, right? Where the energy is constant. So for gallium arsenide, it is spherical, so it look like s orbital, right? For germanium silicon, it look like p orbital. Now you notice one more thing here. This is elongated, right? So along the longitudinal direction, mass will be less or more. Along the transverse direction, so which mass will be more, longitudinal or transverse? Curvature is less along longitudinal direction. Along the transverse, curvature is more sharp. So longitudinal mass will be more. You can see here is 1.64 for longitudinal mass, 0.082 for transverse mass. Similarly, you can see for silicon, longitudinal mass is more than the transverse mass. Right? This longitudinal, this is transverse. In case of gallium arsenide, this is basically spherical, so there is no longitudinal transverse. They are same basically. And here the mass is for light hole and heavy hole. Heavy hole mass is usually more. Light hole mass is effective usually less. Okay. Now let us visualize more how these values look like. So, for example, for germanium, these minima of the bands are along the L, but they are at the exactly at the L boundary, right? So that means this valley will be shared by neighboring unit cell, right? So that means effectively it will, there are 8 L values, right? But per unit cell there will be only 4 L values because they are shared by the nearest neighbors. In case of silicon, there are 6 values and they are inside particular cell. So for silicon, there will be 6 X values inside one cell because they are not exactly at X. They are slightly before X, right? So effectively for germanium, we will have 4 values, 4 L values. For silicon, we will have 6 X values near X values. Now this is for the conduction band. Now balanced band looks more complicated, right? So this is a balanced band surface, and it is given by some complicated equation here, where these parameters are listed for silicon and germanium. So because they are derived from p orbital, so they are more complicated. We will not go into it, but this is just to give you a complete picture how these balanced band and conduction band surfaces look like. So in summary, electron can sit in a specific energy bands, and these bands are numbered 1, right? Band 1, band 2, band 3, band 4, right? Now these each band can have a specific values, right? At gamma valley, X valley, L valley, right? So only bands which are near the Fermi level, right? They actually contribute in the conduction of current. Now we have we can recall also that in case of metals, these bands are basically Fermi levels are inside the band, right? So they can also be represented like this. These are the bands. So in metals, these Fermi levels are inside the band. In semiconductors, these Fermi levels are between the 2 bands, right? So that means at 0 Kelvin, they are actually insulators. Now higher bands, they are of course difficult to visualize, and we have also seen that how the constant energy surface look like. So that way we have completed the lecture on band structure. Now next lecture will be on the density of states and how we are going to fill them. So that is basically carrier concentration. So I rest this class here, and I'm ready to take any question if you have. And otherwise we will take 5-minute break. So it's 11:50. So we will start next class at sharp 11:20. Okay, thank you.